And now for this month's speaker. Last May, I contacted NASA's Public Relations and Speakers Bureau to request a speaker for a future CAS meeting. They introduced me to Mr. Daniel Limonadi from NASA's JPL Jet Propulsion Laboratory. In a few emails, I explained the CAS audience, and Daniel asked what topics we might be interested in hearing. I suggested a discussion or presentation on a planetary system, and Daniel offered the topic Jupiter and its minions. What I didn't know at the time was Daniel was going to research and create a presentation just for CAS. Wow. It's my pleasure to introduce Mr. Limonadi. He's been at JPL since 1999 and is the Chief System Engineer for the Earth Science and Technology Directorate. He describes himself as a lifetime-long space geek with a passion for STEM outreach. Ladies and gentlemen, Mr. Daniel Limonadi.
Thanks for the kind introduction, Kevin. So my name is Daniel Limonadi, as Kevin just said. I'm here from JPL, and I'm here to talk to you about the awesome Jupiter system. It was great doing the homework for this talk. I learned a lot about Jupiter. I mostly do planetary and Earth exploration, so this was fun to kind of take a little bit of a deep dive into. All right, so the things we're going to hit today, 5 major topics. Why do we care about Jupiter? We'll hit some of the earliest observations, including Galileo's observations, right, which were groundbreaking scientifically, as well as from implications for kind of politics on the planet. So we'll have a little go down the rabbit hole on that a little bit. We're going to hit the space age and modern observations. That'll be the bulk of the material we hit today, and then we'll talk a little bit about habitability, especially of Europa, and also implications of what we know about Jupiter for exoplanet systems in general. So why do we care about Jupiter? There's many reasons, right? First one is it's a time capsule of the early solar system and is a model for how gas giant exoplanets work, right? So there are thousands of exoplanets that we know now. Many of them are gas giants. So, it's obviously important to know what we think those do. So studying Jupiter helps us with that, and it helps us understand the early solar system because Jupiter is a very primordial body, hydrogen, helium, and chemistry there helps us understand what was maybe going on with the early solar system. Understanding giant planet formation is also really important, right? So we have actually a mission, Juno, that we'll talk about later in the talk that's dedicated to studying this particular topic, and helps us then again model of how our solar system formed. Understanding how Jupiter formed gives us more insight into our solar system formation, as well as maybe other solar systems that we see now with telescopes, right, the exoplanets. And one of my favorite topics, the roles of moons and habitability, right? So Jupiter has 92 moons. We'll talk about those in a second. Many of them are very diverse. Some of them have ocean beneath, like ice crust. They have probably liquid water, right? So there's implications for habitability there. So we're very interested in those moons. And again, interested in what maybe as a result exoplanets might have as far as, I guess the moons of exoplanets and their habitability zones, which might be larger than just regular terrestrial planets if you didn't take into account the moons of these large planets. So I think a great example of that is the movie Avatar, if you saw that. We'll talk about that later. And then planetary system architecture. So our solar system looks the way it does substantially because Jupiter exists in it, right? And has such a huge gravitational influence. So understanding Jupiter's gravity and how it impacts its own dynamics in detail teaches us a lot about our own solar system. And again, that teaches us about how other solar systems might evolve as well. All right, a little bit of a deep dive into the moons, the big moons of Jupiter, the Galilean satellites, right? So what you see on this slide is Io on the right. It's the closest moon to Jupiter. And then moving out from distance, Europa, Ganymede, and Callisto. These bodies are all large bodies, right? If you compare them to the Earth's moon, every single one of them is bigger than our moon, except for Europa. And actually 2 of them, Callisto and Ganymede, are larger than Mercury, right? So these are all minor planets in their own right. In effect, the only reason they're not planets is because they're gravitationally stuck around Jupiter and not floating around the solar system on their own. If they were in the solar system, they'd be their own bodies because they're big enough. So fun facts here, right? You can see these very different features. Io is this kind of pizza surface moon, right? It is the most volcanically active body in the solar system. And even though this is showing Earth to scale on the right, pretend this is Jupiter, right, which is much larger. What's happening with Io is the three moons on the left, Europa, Ganymede, and Callisto, basically tug on that moon and flex it tidally a lot, and it keeps it very active, pumps a lot of energy into the moon, and basically means that the moon is like spitting its inside out all the time. There's like up to 200 active volcanoes on Io, and it's a cool body from that perspective. So the other moons, the rest of the 92 moons, are kind of left of Io, and they get gravitationally less stressed, right? So Europa still has a decent amount of tidal forcing, this tidal gravity stressing, and we think it's got a substantial subsurface ocean with a thin ice crust. And Ganymede and Callisto might also have subsurface oceans, but because they're getting less tidally stressed, we think their ice crusts are probably a lot thicker, and which is why you can look at Ganymede and Callisto. There's tons of asteroid impacts that you see here, right? A lot of craters versus, Io has no craters from asteroids. It's all volcanic. Europa has almost no craters from asteroids. It's all because it's resurfacing all the time, but these guys are not resurfacing, right? Ganymede and Callisto are not that much older. Anyway, we'll talk more about Europa at the end of the talk when we hit habitability. And just for comparison, how do Jupiter's moons stack up against the rest of the solar system? So the 4 Galilean satellites actually are 4 of the top 6 moons in the solar system from a size perspective. You see Ganymede, Callisto, right? Titan from Saturn, another awesome moon. We could spend an hour talking about that. But that's number 2, and then you got the other guys, Callisto, Io, 3 and 4, and Europa at number 6. Another fun thing about Jupiter is it has a huge flock of Trojan asteroids, right? So there's some interesting gravity dynamics where every planet in the solar system has some asteroids kind of trailing and leading it in their orbit, right? So if you looked, you could make a plot like this for Earth and Mars, and you would see maybe some small herd of asteroids in the Lagrange points leading and trailing the body. But Jupiter, because it's the giant, right, it's the big kahuna in the solar system, has by far the biggest flock. And so that's kind of another interesting thing to study. And we actually have a mission called Lucy that's going out to the Trojan asteroids and studying some of them. And just if you're interested, this graphic that's repeating here shows one Jupiter orbit around the sun, which is roughly 12 years or so, plus or minus. I forget the exact numbers, but kind of a cool graphic just to see inner solar system dynamics as well. And between the red bands here is kind of where the main part of the main asteroid belt is. Okay, early observations and thoughts. So I think you guys are all amateur astronomers. You probably know this better than anybody. Ever since humans basically evolved, right? We've been looking at the stars and have noticed that there's at least 5 bodies, right? The 5 naked eye planets that behave differently than the rest of the stars. So we think humans took notice of that probably tens of thousands of years ago. The first recorded observation that survives kind of from antiquity is from the Babylonian times in the 7th to 8th century BC. So, ever since the beginning of human history, people have been paying attention to the planets and trying to figure out what they mean, what they're telling us. That evolved over time, right? As civilizations got a little bit more advanced and observations picked up, right? People started making different models of how we thought the universe worked. And most of you are probably familiar with the geocentric model, right? So it turns out mostly ancient Europe and the Middle East had developed a geocentric model. I'm going to hit in a second. Turns out Asia and China had different models, right? We'll just a little teaser there. So the geocentric model, if you don't remember, basically Earth is the center of the system, right? One of our early kind of chauvinistic views that humans are special, right? Is we thought we were the center of everything. The planet we live on is the center of everything because our God loves us and must make the whole universe for us, right? So anyway, you can see that the key points for that model here. This was the predominant description of the cosmos, right, in many European ancient civilizations. So both Aristotle and the Greeks, Ptolemy and Roman Egypt, as well as the Islamic civilizations during the Islamic Golden Age kind of all followed the geocentric model. It turns out there were doubters, right? Some people kind of said, "Gee, this seems like an overly complicated system, coming up with these like circles, orbiting circles, to try to explain the motion of the planets." But anyway, the geocentric model was the one that kind of won the day. And one thing that's interesting is the Europeans really focused. They try to make a model that explained the why, like why do the planets move the way planets and sun move around the Earth the way they do. It turns out the Chinese, at least according to Hong Kong University, where I found this little summary, didn't necessarily focus on making a model that explained the why. They were just trying to make observations that were accurate and just capture them. So the Chinese had multiple different models of how the universe worked. They were also geocentric in the sense that there was a flat Earth in the center of them, but they had an infinite cosmos and kind of a heaven, maybe projected above that, but a flat Earth, and basically a flat Earth inside some kind of sphere or circle was their model, but different. I guess the main difference was there was a flat Earth, or maybe I guess that wasn't different. Actually, I guess the late geocentric did have a circular Earth, right, a spherical Earth. Before Galileo came around, right, we were exploring the planet and realizing the Earth was a sphere. Anyway, so the Chinese had a flat Earth model and this infinite cosmos versus the Europeans had mostly the geocentric model with a finite cosmos. So interesting to kind of note the differences there. Of course, then along came Copernicus in the 1500s, and he was probably the one to most forcefully push the heliocentric view of the solar system, which others had as early as the 4th century BC, but he proposed this much simpler way to describe the motions of the Earth and the planets. It was kind of poo-pooed for a long time until, right, the hero of our story, Galileo, showed up. So in 1608, if you guys remember, the first telescopes were actually built, and I'll show you the timeline in a second. Galileo got his hands on some early models, and I think there's some reports that said he might have made his own. And you see a couple of examples of Galileo's satellites in a museum in Italy on the left. And in 1610, he pointed one of his telescopes, a 20-power telescope, at Jupiter and made these sketches. You can see, so this is January 12th, 13th, 15th down here. I guess, or maybe 14, 15, 16, 17. And he just sketched what he saw, which of course kind of blew his mind, right? That he saw, just like we can today, right? If you get some high power binoculars or a basic telescope, you can recreate what he saw. And I'm sure you guys do this all the time. He saw other things, kind of obviously going in orbit around Jupiter. And that, was a huge day for science, I guess the beginning of science, and this data-driven approach to how we view the heavens, right? And so Galileo captured those thoughts, like his data, wrote about that, and for various reasons, after a while, he was persecuted by the church, right, as part of the Roman Inquisition or the Roman Catholic Inquisition for his views. So that's a whole nother like fascinating little story. But the bottom line is he managed to, like, the Pope kind of left him alone for the most part, but then at one point he managed to piss off the Pope, and the Pope couldn't let that slide, so they prosecuted Galileo for his heretical views on how the universe worked, and he was put in house arrest for a while, basically till the end of his life, right after that. This just kind of puts Galileo's position in the scientific revolution in perspective. This was again like another fun little deep dive for me. But if you remember, so on the left here, the left green hand box, we're going from 1525 to 1725 here in this timeline. Copernicus published his theory in 1543. There wasn't really much new data to back it up. And then, so Lippershey, right, came up with the first refracting telescope in 1608. And Galileo then used those observations, as we just talked about, to publish his findings. And that really led to Kepler, right, coming up with the laws of planetary motion, and also Francis Bacon in 1620, basically, really cementing the scientific method, right? So this was a huge deal, and I'll talk about that in a couple slides. But the scientific revolution led to the just the revolution in political thinking on Earth as well, right? So it had a lot of implications. As a fun side note, I remember somebody told me a while ago that he thought the rise of coffee consumption in Europe also played a role in the scientific revolution. I did a little homework, and it turns out that really wasn't the case. So, Asians were drinking tea for a long time, but the first tea that was consumed by many people, so the first coffee houses, didn't really show up until the mid 1600s in Europe. So a lot of science stuff was going on before coffee and tea houses showed up. So anyway, fun stuff. Bottom line is observations of Jupiter helped push the scientific revolution and change the course of politics on Earth, which I'll talk about a little bit more in a second before we move on to more observations. And then kind of nothing happened, right? So 1610, 4 moons are discovered, and no new moons are discovered until 1892. Amalthea was the next moon, and then a string of other moons, and by 1951 there had been roughly 12 moons of Jupiter discovered, right? So that's really kind of near the beginning of the space age. And the next ones weren't basically discovered until Voyager showed up. So that takes us through kind of the end of early observations, beginning of the space age. All right, so this is Sputnik 1 launch. So now I'm just going to kind of go through some of the different spacecraft missions that came through and explore the Jupiter system and what they discovered. So Pioneer 10 was the first mission, a flyby mission that launched in March of 1972, a couple months after I was born, and flew by Jupiter in December 1973. So a couple of things to highlight here. We're going to be looking at different spacecraft pictures as we go through this time history. And one thing you're going to see is the flyby missions all have this kind of same form follows function layout, right? So there's usually a very large antenna because they're going very far from Earth. So you need a large antenna to try to have any kind of data rate, usable data rate to get back to Earth. And then because they're trying to just get out there at a reasonable cost, and they're not orbiting, they don't really need any fuel. We just kind of chuck them out into outer space with a big rocket. They have maybe a tiny propulsion system. So they're very lightweight, right? It's a giant antenna. In this case, there's nuclear power supplies, these RTGs, radioisotope thermal generators, and some instruments, magnetometers, or these big long skinny things, right, to get the magnetometer away from the magnetic spacecraft, so it can make measurements, like less contaminated measurements of space. So anyway, you're going to see similar form factor for later spacecraft. Because we knew Pioneer was the first human-made vehicle that was going to leave the solar system, they went ahead and put a plaque on, kind of a symbolic plaque on the outside of the Pioneer spacecraft, kind of showing position of the sun relative to the nearest 14 pulsars in the center of the galaxy, right? So if somebody else found this thing, right, this was effectively like our first take at extraterrestrial communications. Hey, in case somebody finds this thing a million years from now, here's a little bit about us, right? Anyway, so kind of a fun thing. I won't go into details there, but we had that plaque on Pioneer. You'll see another one on Voyager. So the mission of Pioneer was to explore the asteroid belt and Jupiter. It had a pretty crude camera on it. It was the first spacecraft to travel through the asteroid belt and kind of make it out alive, right? We weren't sure if that spacecraft would make it, like how dense the asteroid belt was, how much small stuff there was. And it turns out, space is big, and even if you got a lot of tiny particles, you're unlikely to get hit by something that's going to kill you. So we started kind of getting evidence for that, with Pioneer, and it made the first observations of Jupiter. You can see this artist rendition here on the left of the Pioneer 10 mission with this kind of hand-drawn Jupiter thing. So it detected Jupiter's magnetic field, observed the radiation belts, the intense radiation belts of Jupiter for the first time, and just from visible data and other things kind of determined that it looked like Jupiter was mostly fluid. And you can see here, these are pictures taken by Pioneer on the right. And I think we're going to look at some pictures later, and you guys might even have your own pictures, right? I think today, amateur astronomy telescopes can take pictures like this well, right? Like you didn't need to send, wait 60 years, and ground-based telescopes, cheap ones, can do the kind of some of the science that Pioneer was doing. Obviously not the magnetometer, not some of the in situ science, but anyway, so kind of fun thing there. Then Pioneer 11. So Pioneer 11 was basically the twin of Pioneer 10 launched about a year later, and it was the first spacecraft to take advantage of gravity assist. So this is, you're seeing Pioneer 11's trajectory through the Jupiter system, right? Callisto, Ganymede, Europa, Io from the outside in. And then the little hash lines are, it's below the ecliptic plane. And then as it passes Jupiter, it goes above the ecliptic plane. I didn't grab the animation, but basically it uses a slingshot past Jupiter to then make its way to Saturn. And took, roughly the same kind of data, right? And both Pioneer 10 and 11 lasted a long time. So they lasted till the 90s, basically mid 90s, when the power from the nuclear power, the little decaying plutonium that was its power supply, wasn't enough to keep the thing going. But cool missions last a long time. So another fun little human story here. So Ames Research Center, so I'm a JPL guy, right? Ames is the other NASA center in California, up in Northern California, in case you're not familiar with them. They used to be actually decent players in planetary exploration. I think these days most people think JPL has done the vast majority of NASA's planetary missions, and but that wasn't always the case. So back from 1962 to 1980, there was a Pioneer Program Office at Ames run by Charles Hall, this guy, picture on the right, he looks, kind of the classic picture of a steely-eyed missile man from early NASA, right? And I don't know if his nickname was Chuck, but Charles Hall really did a great job managing the Pioneer missions, keeping them kind of on cost, and basically sacrificing scope. So if, instead of having maybe the world's best camera, if we need to stay on budget, then he, got like an off-the-shelf camera to do kind of good enough science, right? And in the early days of the solar system exploration, when you kind of didn't have any data, that was still good enough to advance technology forward. Once you've done that initial science, doing future stuff, you kind of needed to get better and better instruments, and those got a lot more expensive, and cost overruns and stuff like that kind of became a little more commonplace. But kind of kudos to this office and Charles Hall at Ames for kind of doing this early stuff, and also TRW, now Northrop Grumman down in El Segundo, built Pioneer 10, 11 under Ames management. So that was kind of a cool little thing. So the next big thing, and again, if you guys have questions, just let me know or scream or something. Somebody can maybe relay or raise your hand or whatever in Zoom.
Hold on 1 second, Daniel.
Sure.
Oh, sorry. Yeah, I think we're good on questions. There were a few. We're just checking the chat. If people are having trouble seeing, but we since resolved that. And a note about the size of the moon relative to.
Okay. And then when you get a chance, Daniel, I do have a question. So with all of those moons around Jupiter's a gas giant.
Yep.
Do the moons tend to be terrestrial, or are they gas, or?
They're all ice and some rock, right? So icy, rocky bodies. Just because, Jupiter's got, it was there early in the solar system. It kind of grabbed all the local gases around it, but the moons did not. If they had any gases early, they didn't hold on to their gases because they're a little bit too small to hold on to their gases. Plus, you got giant gravity from Jupiter kind of sucking stuff away, and also Jupiter's radiation field putting a lot of energy into things. So I actually don't know if we think that maybe some of the big moons might have had gas early. But you look at Saturn, Titan does have an atmosphere that's about the same, like 1 bar density, or pressure. So there are, there's an example at Saturn where that moon held on to its atmosphere. I think Titan is maybe further away than most of the Galilean satellites are from its like host planet. But anyway, yeah, good question. Any other questions?
Let me see if anybody else has a question. Anybody else? All right, we're good for right now.
Okay, cool. Thanks. Okay, so then we move on to Voyager. This is basically, Pioneer on steroids. So you see the same form factor, right? Big antenna, magnetometer boom, this time bigger RTG. So we have a lot more instruments on Voyager, higher quality cameras, UV spectrometers, all kinds of other stuff here. And so you need more power. So they had 3 of these RTG pucks basically. And Pioneer, I think, only had 2 distributed, right? So we launched those 1977, at least Voyager 2, 1970, in August 97, and then Voyager 1 was actually launched second in September of 1977. And I think you guys know, right, the Grand Tour. So both of those were designed to explore much of the solar system, Voyager 1, I think, did just Jupiter and Saturn, and then kind of was ejected. And Voyager 2 went on to do Neptune and Uranus and other stuff as well. So here we have kind of the next step up from our little message to the cosmos, right? So Pioneer just had that simple graphic. And for Voyager, we actually put a record. This is a golden album. And the info on this album actually shows you, it's literally like it's a like vinyl, right? So that it's etched with music and other data. And the info on this album cover, so to speak, tells you how to try to design the sensor to listen to the music. Right? So it's like how to make a record player, basically, is try to, like, in very simple ways, they try to like put a little code in here that might be universally understood by who knows who for how to play it. And again, the same image of like where our solar system is relative to the nearby pulsars. So kind of fun. And Carl Sagan pushed this one. I think Carl Sagan might have also pushed the Pioneer. He was kind of one of the motivating people behind getting these things out. So anyway, so that's Voyager. This is the Voyager 1 approach, kind of like, as it's coming in. You just made a little animation of the approach images as it's coming in. You make a little movie, right? Kind of cool little movie. And so Voyager did a bunch of cool science, right? Even though it was also just a flyby mission, they discovered the volcanic activity on Io. So it turns out Io is the most volcanically active moon in the solar system. We'll see a picture of that in a minute. Actually discovered or confirmed Jupiter's ring system. I kind of got some mixed messages there. I think it might be discovered. And then, did some nice, more detailed analysis of the Great Red Spot, discovered a few more moons. So we were at 12 up until this point, and 5 more were discovered, I think 5 by Voyager. And again, did some nice detail imaging of Europa, Ganymede, Callisto, and try to confirm that these are really cool moons that we should check out and help motivate the Galileo mission that I'll talk about in a minute. So, and just the quick little side thing, if you guys aren't aware, we have 5 spacecraft currently that have basically like achieved escape velocity from our solar system, right? And they're going to be kind of humanity's messengers to. So even if we die tomorrow, we've got some space junk on its way out to different corners of the local galaxy that will be some testament to the fact that we were here, right? So Pioneer 11 and 10 kind of in these opposite directions, and then Voyager 1 and 2. The Voyagers are currently the furthest thing out, and New Horizons, I think, will eventually catch up and beat them because it was going faster. New Horizons also did a flyby of a Kuiper Belt object, another fun thing to talk about, but we're not going to time for that. That's not our talk today. So next mission, so remember the last flyby was 1979, the Voyagers. The next dedicated mission was Galileo, launched in 1995. And what you see on the right is a little animation of the approach vector of Galileo into the Jovian system. And then it's kind of initial few years of, actually, I think it might have been the whole mission here. You're seeing like all the orbits around the Jupiter system from Galileo. And the one thing that's very quickly different, right, is these spacecraft, like Pioneer, Voyager, are few hundred kilos kind of spacecraft, right? They're fast. You're chucking them out there and they're fast flyby missions. And now with Galileo, you're starting to do orbiters. You need a ton of fuel to get yourself in orbit. So there's a huge propulsion system in the middle of this thing, right, that the flyby missions don't have. And again, bigger instruments. There's also an atmospheric probe that was attached to Galileo that entered the atmosphere of Jupiter, made some direct measurements of the atmosphere and stuff like that. So much bigger mission, right? These are more like 5 to 10,000 kilo class spacecraft as opposed to the few hundred kilo, half a ton class vehicles that we were looking at before. So Galileo launched in 1989, arrived at Jupiter 1995. And then because we learned so much about Europa and thought Europa had a high chance of being habitable, and we'll talk about that later in this presentation, we actually basically disposed of Galileo by trucking it into Jupiter's atmosphere and letting it burn up in Jupiter's atmosphere. Because we didn't want to have it risk, like if we left it in just orbiting randomly around Jupiter after it died, it might crash into Europa, and we didn't want to kind of contaminate Europa with Earth bugs to mess up our science. Eventual, like we want to go to Europa and land on Europa and do other stuff, and we didn't want to kind of mess up that science. So again, so Galileo is also the first orbiter, right, of the Jupiter system. So some of the cool stuff we learned from Galileo, one, Europa, strong evidence of a subsurface ocean at Europa. So Europa is this body on the lower right hand. It's the second moon of Jupiter. It's also got the youngest surface in the whole solar system. So it's basically ice crust that's continually kind of refreshing itself. And so, right, a lot of evidence that not just that there's an ocean, but that the ocean has come in contact with the surface and melting or doing other stuff to kind of erase craters on the surface. And then we also, again, confirmed and got a really good look at Io's volcanic activity. So this upper right-hand picture is, we kind of lovingly call the pizza moon, Io. It's got, like, it's the most volcanic, the active body in the solar system. And it's just got sulfur and other compounds here that kind of create these crazy colors. And it's just, I think it's got like probably order of a dozen, at least one giant volcano erupting at any point in time, and then usually like dozens of smaller ones or whatever, maybe going on at a time. And what's driving that is the tidal forces of Jupiter. So it's a little hard to see in these pictures. But Jupiter's the green guy here, right? And so Io is the first planet. And so Jupiter's tugging on one side, and the other moons, Europa, Ganymede, Callisto, are tugging on the other side. And so it's like squeezing a tennis ball with your hand, basically. The moons are squeezing that moon. Sorry, the other moons are squeezing Io and pumping it full of energy, basically from that squeezing, right? As you're like scraping rock and stuff like that, it's heating everything up and making this, relatively molten planet. We also discovered a magnetic field around Ganymede, and then Jupiter. We sent a probe into the atmosphere, made the first detailed measurements of the composition of Jupiter's atmosphere, weather patterns, other stuff, and again we confirmed the rings and what they were made out of, these dust particles ejected from the smaller inner moons. So meteoroid impacts hitting the small moons are making the faint ring that Jupiter has. So that's kind of the highlights of the Jupiter mission. The Galileo mission. Again, this ended early 2000s. It also had its trials. So a couple things. It was originally supposed to launch, mid like 1986, 1987 on the space shuttle. The space shuttle Challenger accident happened in '86, and that messed up its launch date. It ended up not launching until 1989. And then again, took 6 years to get there. And then there was another, right? The real bummer was because the vehicle was in storage for so long because of these launch delays. The antenna had this big deployable antenna. Unlike the previous missions, which had rigid mount antennas, this was a deployable antenna based on some other successful technology NASA had. But it got stuck. The lubricant kind of like migrated, so we couldn't deploy this high gain antenna. So we had to do the whole mission. Instead of a data rate of 134 kilobits per second off this high gain, we had to use the low gain, these dinky little low gain antennas, and took like factor of 1,000 hits a data rate. So the low gain antenna original data rate was supposed to be 8 to 16 bits per second, but once we learned shortly after launch this high gain was not deploying, the JPL and NASA went into overdrive to try to get as much out of that low gain system as we could, made modifications of the deep space network, updated software, the few lines, I think there's like a few kilobytes of memory on the computer, on that vehicle at the time, right? Early computers, updated the software to do kind of more efficient encoding of the data, and then built really sensitive receivers on the deep space network, antennas on Earth, to really kind of milk all the energy out of every transmitted bit to increase the signal and noise. And we got the data rate up to about 160 bits per second relative to the original 16 bits per second, which made the mission viable. And we still got 90% plus of the science return from the mission based on saving it with the low gain antenna. So that kind of caused a lot of stress and blood, sweat, and tears for a lot of people to kind of deal with that obstacle, as well as all kinds of obstacles, right? Building these things is always really hard. Anyway, then we move on to New Horizons. So this is another flyby mission. New Horizons is a Pluto flyby mission, but it used a Jupiter gravity assist to do its thing. And this was a cool, basically animation. It just took a bunch of pictures really quickly. On its way past the Jupiter system, it was targeting Io and saw this like just awesome kind of stop motion video of this huge volcanic eruption on Io, right? So you see, this is, I'm not trying to pronounce this correctly, Tavashtar volcano, right, with a plume that's going 200 miles, 330 kilometers up above the surface of the moon. You know, relatively low gravity, high energy volcano, and you know, just really cool little data point from that camera. So again, New Horizons, it's a flyby mission. It looks more like the other ones that you saw, Pioneer, Jupiter, and Voyager, right? So little compact thing, fast, you know, trying to get to the outer solar system quickly. It had an RTG like the past missions, and it had, you know, a handful of different instruments. And another fun fact, right? So this antenna that it had, Jupiter is so much closer than Pluto. They actually took more data of the Jupiter system than they took of the Pluto system because they could, right? They could get a lot more data back because you know, the data rate was a lot higher from Jupiter. And then around the same time frame, 1990s to today, we also started getting, you know, substantial space telescopes, right? So let's see, speed up a little bit here. So in the upper left, right, we have Hubble and James Webb today, right, taking pictures both at the same time. But for most of the last few decades, it's been Hubble. And one of the fun things that Hubble saw, so what you see here, upper left-hand side, is these like stretched images of Europa. This is Hubble images of Europa, pretty high resolution, right? Really cool. But trying to really draw out all the possible light. And so you see the background stars just kind of all smeared into kind of a soup. And you can see these plumes, right? So they kind of went plume hunting 2014 and 16. And it looks like we see evidence of plumes like erupting on Europa. And we'll talk about why that's cool in a few slides. So Hubble did that. Also with studying Jupiter itself, both in the UV, visible, and near-infrared light, you know, 2020 and other years, like once a year or so, Hubble would take pictures of Jupiter and other moons to kind of track what's going on. And then this is one of the pictures from James Webb. So higher resolution, it only does infrared, higher resolution infrared than Hubble. And you see other bunch of stuff, right? Because so infrared is kind of seeing thermal emissions, not just reflected light. So you see some of thermal emissions and reflected light maybe from the faint rings and some of these other small moons out here. So cool stuff there. Okay, next mission. So Galileo, again, went in the drink, right? It died. We killed it on purpose, early 2000s. Next mission that went to Jupiter was Juno. This is a Jupiter orbiter mission that I think Goddard Space Flight Center and Lockheed Martin worked on together. And this, now what you see, so different form factor, right? So previous to this, all the missions out to Jupiter and beyond were nuclear powered missions. So using the waste heat of plutonium to power the spacecraft. And by the 2000s, you know, early 2000s, our solar cell technology was getting good enough that we could put solar panels on spacecraft and power them at Jupiter. And so that's a lot cheaper and easier from a regulatory perspective. Putting nuclear stuff on a rocket is a big headache, paperwork-wise, risk-wise, and other stuff. And so preference is to do solar panels if you can. So starting with Juno, we've been putting all the missions to Jupiter are solar. So they launched in 2011, got there in 2016, and really was focusing on understanding the origin and evolution of Jupiter. And what you see on the right-hand side is basically all the orbits of Juno through basically the modern time, from when it arrived to now. And you can see they're in this very highly elliptical orbit around Jupiter. One of the reasons we do that is Jupiter is a really, really, really nasty place, right? So if you're within minutes, if you're a human and you're close inside Jupiter's radiation belts within like the orbit of Europa and Io, you will die. Like you get lethal dose of radiation within minutes, if not faster. I forget the exact time, right? And same thing for modern electronics. They really don't like being in that environment. So this mission actually had a vault. And anyway, so they fly far away, use this time out here to transmit the data, then come back in, get a bunch of new data, and then transmit the data when they're far away and kind of do their mission that way. Here's all the stuff that Juno discovered. More information about the core of Jupiter, discovered lightning on Jupiter, more information about the magnetic field, that it's stronger than our previous models predicted, right? We had better magnetic sensors on Juno, a bunch of stuff about the atmosphere, and also saw aurora. And this is a really cool So there's a camera on Juno, and it's an outreach camera. So they try to make it cheaper, right? This was kind of a fixed price mission. And they, in order to save money, they didn't make the camera a science instrument, which would have to jump through a bunch of hoops for science quality and stuff like that. This was kind of a bonus outreach camera, like, hey, if it works, that's great. If not, we don't worry about it. And this is an image sequence from JunoCam of one of Juno's flybys, right? So this is 29 September 2022. And when I saw this, when I was doing homework for this talk, it just kind of blew my mind. I mean, that's just awesome. Really cool. I mean, to me, it makes you feel like you're really there, right? Like just really, really neat. And you just realize like how big that planet is. And all the cool features and stuff like that that you see there. So you can find that online if you want to look at it. And you can see the funky, one of the things we've been doing with Juno is you can see that like these really weird circulation patterns at the poles, North and South Pole. I think we see it on the other side as well. Yeah, coming in here. So this like really crazy kind of chaotic atmospheric circulation at the pole as we're flying by, and then going through there. So fun stuff. So Juno's still flying today, and I couldn't find. They don't have a date yet for when it might be end of mission for them. So that's kind of there. So now I'm going to jump to ground, like kind of next tranche of ground-based telescopes, right? Stuff you guys might be more familiar with. So there's tons of big telescopes, as you guys might know, right? This is from Wikipedia, kind of list of large telescopes just by size. Currently, the biggest ground-based telescope on Earth is this effective aperture 11.9 meters is actually the large binocular telescope. It's two 8.4 meter telescopes next to each other. You can kind of see this little image maybe. And these things all take pictures of the planets and other stuff, right? So they're imaging our planets, other stars. You guys are probably familiar with some of the data from these guys. But they've kind of peaked out, just kind of interesting. Most of these 8 to 10 meter telescopes were all built kind of late 90s, early 2000s. And for the last 20 years, the big telescopes that we've been working on funding and trying to build 30 meter telescopes, and I'll get to those later. Those are not operational yet. So just one fun thing, kind of an ode to the amateur astronomer, right? I thought this was an amazing, I mean, you guys probably have lots of these in your club, right? I'm sure. This is a time lapse taken by an amateur astronomy guy with that tagline or handle on Reddit space in 2023 with his 10-inch Dobson. And it just kind of blew my mind, right? The quality of those images and what folks are doing now just with amateur astronomy. Again, as good as probably the pioneer images, right, from the early 70s. So that was just really cool. This is what you can do with a 8-meter telescope, Gemini. So this was a Gemini infrared image taken in April 2019. So I just kind of wanted to give an example of like what you can do with a modern, large diameter telescope, near infrared. And because Hubble is still taking better optical images, a lot of times what people do is like merge these things with like Hubble optical, like you see here, Hubble RGB and ultraviolet. And then you kind of merge that together with the infrared that Hubble can't do from the Gemini instrument and get these composite images to try to get more insight into what's going on inside the planet and stuff like that. So a lot of cool things that people have been doing with ground-based telescopes and combinations of ground and space-based telescopes. And then here's the little, the teaser. Again, you guys probably, I'm guessing maybe somebody's talked to you guys about these, right? There are 3 order of 30-meter telescopes that are getting built right now. The TMT 30-meter telescope, the Giant Magellan telescope. I think those are northern and southern hemisphere, and then the European extremely large telescope, right? Those are all under construction, various phases of planning and construction. The ELT, the European extremely large telescope, is supposedly, I think per the Wikipedia thing I was looking at, aiming for first light in 2028. So these things are going to supposedly beat Hubble in angular resolution, but we'll see. I'm not sure if I 100% believe that, but they say they will, with the adaptive optics and stuff like that. Right? Remember, Hubble is like order of, I think, 2.5 meter telescope or something, but because it's above the atmosphere, right, it's getting very clear images. So the ground-based telescopes have, all have to have these laser adaptive optics techniques that you guys, I'm sure, talk about. to kind of try to reconstruct and get some sharpness back from their big collecting surfaces. So, but anyway, hopefully with these larger telescopes, we can do some limb sounding. Like you'll actually be able to kind of split the atmosphere of even some of the moons into a few pixels and do effectively limb sounding, spectral limb sounding of some of the moons and giant planets and stuff like that. So that's gonna be cool. And then quickly going through some of the future missions. So we just launched Europa Clipper. This is a JPL mission. It is a giant spacecraft. I think it's like close to 10,000 kilos. So a bunch of friends of mine worked on this. I did not work on it. And you kind of see the normal magnetometer, bunch of, the kind of world's most modern, deep space instruments, cameras. We actually have a ground ice penetrating radar on this, a low frequency ice penetrating radar called Reason, and other instruments. And again, to avoid kind of dying in the radiation of Jupiter, of near Jupiter, we're doing flybys. So it's a Jupiter orbiter, but it's doing a bunch of targeted flybys of Europa, and you can kind of see these the like flyby geometries in this image on the right. And even with that, trying to keep distance most of the time from Jupiter, we still get a really high, like 2.1 megarad total ionizing dose during the prime mission. So over these 45 low altitude flybys over 3.5 years. So that's going to be really cool to see. I'm really looking forward to that, but it's 2030s when they get there. The Europeans launched JUICE about a year, April 23. It's, so we're targeting Europa with Europa Clipper. JUICE is targeting Ganymede. It's going to eventually get into Ganymede orbit around 2034. It shows up at Jupiter at 2031 and then does a bunch of like funky gravity assists and kind of tours the Jupiter system, 35 icy moon flybys to get into that Ganymede orbit with the minimum fuel. So that's going to be really cool, but again, 10 years from now. And then the Chinese are launching something supposedly 2030. Not sure when it's going to get there. Like the Chinese space program is very opaque for the most part. So what I could find is they're doing this Jupiter Callisto orbiter that they're launching in 2030. And right, so we're going to, so sometime in the 2030s, we're going to have kind of a Europa targeted mission, Ganymede targeted mission, and then a Callisto targeted mission, kind of hitting all the big moons. So we're going to have a small flotilla, international flotilla at Jupiter doing a bunch of cool stuff. That's going to be really exciting for Jupiter science. Any questions on that stuff before I jump into habitability real quick? Hopefully people are still awake.
Yeah, we're waiting. Yeah, can you see us?
Okay.
We're still. All right.
Okay.
Back to you, Daniel.
Okay, cool. I'll keep going. So habitability, I mean, this is kind of always an interesting question for anything, right? Like, might there be life anywhere in the solar system, including gas giants? So this picture was actually, I think, commissioned art for the Cosmos, the original Cosmos series that Carl Sagan did. And so he commissioned this artist, Adolf Schaller, to do this. And this is showing, quote unquote, hunters, floaters, and sinkers. So some people's, just kind of ideas of like, hey, what might life if there is life, what might it look like? And the scientific kind of defense of this is, turns out Jupiter and even some of the other gas giants and even Venus, right? On the other side of the solar system, near the 1 bar. So in Jupiter's case, it's like 5 to 7 bars. So 1 bar is like the surface pressure of the Earth at the surface of the Earth. And so at the 5 to 7 bar point, so a little bit, higher pressure on Jupiter, it turns out there is water there, right? And there are water clouds on Jupiter. Not everywhere, but there are, spots with water clouds. Most of the clouds are ammonia clouds, but there's a decent amount of water clouds in this band where water is stable on Jupiter. And so as we've discovered, like over the last 50 years, astrobiology and just life on Earth, we've learned that basically anywhere on Earth, like literally anywhere on Earth where there's water and some kind of battery, right? If some kind of way for nature to make a battery, there's bacteria or archaea, some single cell life at a minimum making a living. And then sometimes obviously multi-cell life chewing on the single cell life or whatever, right? And so, so since there is water in Jupiter's atmosphere, I think you can't rule out at least life as we know it, right? Water, carbon-based life. And so anyway, that's all I say. I mean, there's a lot of challenges, right? There's a lot of radiation there. There's crazy high wind speeds, lots of turbulence, other funky chemicals, which could be good and bad, right, for life. I mean, some of the chemicals there, could be especially trace amounts like, nutrients that life could use. There's a lot of lightning, making energy and stirring things up. And so, again, who knows? We have no evidence for life there now, just to be clear, right? But it might be maybe in 50 years or something, if we can have balloons just kind of floating around in the upper atmosphere of Jupiter and looking for this stuff, maybe we'll find something cool. So who knows? So you can't rule it out. Might be there. Now, Jupiter's moons, on the other hand, totally different story, right? And so especially Europa, it's much more compelling. So Europa, Ganymede, Callisto, they all seem to have at least strong evidence or some kind of evidence for subsurface oceans. And so far from what we've seen, Europa is the most promising. That's why the US NASA is sending that Europa Clipper mission over there. And what you're seeing here is kind of a cross section. What our kind of current models say what we think Europa looks like, right? So it's got maybe a rocky core, kind of a slushy or hard ice mantle, and then either very slushy, mobile ocean, kind of quasi ocean, or actually liquid ocean with some kind of global circulation there. And then it's got, frozen ice crust on the outside because it's really cold. And that frozen crust on the outside is like order of 10 to 100 kilometers thick, right? So everybody at JPL dreams of drilling through this ice and sticking a submarine in that ocean, because that would be the freaking coolest mission ever. But really hard and really expensive, right? So Europa Orbiter is kind of going to do the detailed recon, right? So we've got all this funky terrain that we're seeing on the surface of Europa based on Voyager and Galileo data. And so we kind of want to, and we're going to bring this ice penetrating radar and higher resolution images to really see what's going on here. There's different ideas of what might be going on in the ice crust, right? Maybe a little like, rising quasi melted ice, maybe not. So there might be like lakes of water in the crust. We're not sure. And we think there's probably a briny ocean based on magnetic field studies beneath that ice. Again, maybe it's just slushy, but we think it's probably liquid water. So that's going to be really exciting to kind of get a much better feel for. And with this ice penetrating radar, we're hoping to kind of get to the bottom, like how deep is this hard ice, the dry ice, on top before you hit the ocean. Hopefully we're going to see that with Europa Orbiter. That'll be really cool. Here's another picture again. So the plumes, like, why do we care about the plumes? If there are plumes, it's evidence that, like, literally there's like jets of water, volatiles just coming from the interior and like making their way through cracks in the ice into space at Europa. And, that might mean that there's a sneaky path, right? Maybe we can stick a probe into these like little ice vents or whatever, or like water vents, and try to get in the ocean that way. So it's going to be exciting to kind of try to follow up on that. This is another model of what we think the inside might be. And again, the same tidal friction, tidal forcing that's warming up Io is also warming up Europa, but not so much, right? It's just enough to maybe keep the liquid ocean going. But we think there might be hydrothermal vents there, right? And hydrothermal vents on Earth is a place that life might have started, so we don't know. Anyway, so it's really looking forward to that mission getting there. That's kind of the habitability story, right? So the moons are exciting. Jupiter, even the atmosphere might be interesting. We'll see what's going on when we get there in the 2030s. So now, kind of the last part of this talk, implications for extrasolar planets. So this is a really cool graphic. I'm going to explain it a little bit before I let it go. Of back in 2010, like a summary view of a bunch of the planetary systems we've discovered with the Kepler mission. And I'm not going to go into the details of like how the Kepler mission works, but basically it uses the transit technique to detect planets, and it's very biased, right? So it's biased. It's much easier for Kepler to find large planets close to their parent star. And so what you're looking at here is a model of our solar system. The dashed lines are kind of our solar system orbits, right? So you see sun in the middle, right? Rock number 3 is us. Rock number 4 is Mars. Rock number 5 is Jupiter, right? That's this dashed ring that kind of takes up most of the screen. And then rock number 6 is, or whatever, planet number 6 is Saturn. I'm going to hit play. And right, so this is an animation that just shows this really cool. There's a bunch of stuff going on here. right? Actually, let me pause it. So it's showing what we think the orbits are of all these extrasolar planets, the size, our estimates of the size, and also the temperature. Blue, white is cold, red is warm and hot. And so, anyway, really cool thing, right? And so what you see is there's a decent amount, right? So where's Jupiter moving around? So here's Jupiter on the bottom of the screen, and that's a Jupiter-sized planet. And you can see there's a decent amount of big Jupiter-like gas giants, right, in all these systems. A lot of them are closer. Anyway, the bottom line is it seems like there's a decent amount of gas giants out in the galaxy, at least from our sampling of parts of the galaxy. Some of them are very warm, these hot Jupiters. Some of them are cold. So anyway, so Jupiter is not it's not just a freaky thing in our solar system. We think there are probably lots of places. So again, back to why are we paying attention to Jupiter? Also for extrasolar reasons, right? So again, back to the movie, who saw Avatar, right? Raise your hand. If you saw Avatar, right? So Avatar obviously had, extrasolar planet, a Jupiter-like planet. They try to make it pretty obvious, right? They had this red, giant storm kind of esque thing in one of the opening scenes, and here's the moon, Pandora. And so, that's it's not an unrealistic thing to say that there might be habitable moons, whether it's underneath an ice crust in an ocean, or, if their Jupiter is closer to the star than our Jupiter, right? The moon itself might be might be habitable on the surface directly, right? So, anyway, so hot Jupiters, what do we know, right, from our studies of the galaxy and looking for other planets? We know hot Jupiters are pretty common, but again, a lot of that we think they're common, but you have to take that with a grain of salt, because all the techniques we use right now are either stellar wobble or planetary transit, and they're very biased. Much easier to find big planets close to the star than it is even big planets far away from the star, and much less smaller planets far away from the star. But based on the data we have, we think these are pretty common. There's other studies going on that just came out, I think, within the last year, that thought maybe cold Jupiters, which is like ours is a cold Jupiter, might be in less than 1 in 5 solar systems, but might actually be reasonably common in maybe more sparsely populated parts of the galaxy, right, where there's not maybe a ton of stars all next to each other. I didn't read the details of that, was just skimming that article. But anyway, there's Jupiters all over the place. Maybe not every sun or every star, but probably a decent fraction of them have Jupiters, right? So we care. So everything kind of that we're learning applies, but we need a ton more work here, right? We need big telescopes, and we need to look at these extrasolar systems to understand them more and see how close they are to our system. So anyway, I think that's basically it. So I spent 20 minutes looking for a graphic online of Jupiter and its minions, and this was, I guess, somebody generated with AI, gave AI prompt to some AI graphic tool, and this is what it came up with. So Jupiter and its minions, and that's what I got.
All right, thank you.
All right.
Do we have any questions? Questions? Get your thing.
Oh, I stopped my mic. So that was a great talk. Thank you. You said, I think a lot of us would be interested in the question of life on, for example, Europa. But you said something along the lines of the radiation is so intense from Jupiter's radiation belts that it would kill you rather rapidly. And it sounds like if you had any kind of carbon-based chemistry life, it wouldn't really function in that kind of environment.
Well, good point. It's a good poke, right? Turns out if you're swimming around the ocean, you got a giant shield, right? You got kilometers thick ice above you. And so, the radiation mostly applies to the surface, right? So if you're an astronaut walking around up here, or if you're some single cell life walking around up here, probably not an easy time. Having said that, right, I haven't compared the dose rates, but we know there are bacteria on Earth making a living inside nuclear reactors, right? So there's this bacteria called nicknamed Conan the bacterium, which we think might be the toughest single cell thing that we know of, right? It's got triply redundant DNA, and it fixes its DNA faster than the radiation from the nuclear reactor destroys its DNA. And so it's like making a living inside the nuclear reactor, right? So life finds a way, right? Per the quote from Jurassic Park. And so I wouldn't rule out anything, but you're right. It's probably a rough time up here, especially for anything multicellular, right? Um, but who knows? Maybe single cell, especially like, anyway, right? Enough said. So down here, probably nice, warm and wet. Up here, maybe kind of scary, cold and freezing, and and high radiation. So maybe there's nothing up there. But life is weird, right? Like 50 years ago, we thought life was super finicky, and over the last 50 years, again, like everywhere on Earth that we see water and an energy source, there's some single cell thing, like waving back at the camera, saying, "Hey, how's it going?" and chomping on something, right? So sulfur, hydrogen, whatever, lots of anaerobic energy sources, right? Batteries. And so who knows, right?
So Daniel, in fact, Dave and I were talking about this about 2 or 3 weeks ago. So we happened upon a discussion about tube worms on the Earth that live, what did
Yeah.
you say, it was 300 degrees centigrade?
Yeah.
Very hot,
Yeah.
just below the melting point of lead,
Yeah, you're right. So like, yeah, if you give life, it seems like Earth is telling us, if life starts and you give it time to adapt, like it can kind of adapt to a lot, right?
Gotcha.
And so anyway, right, that we'll find out, right? And that's one of the exciting things. Like I keep telling kids when I talk to kids, I'm like, in your lifetime, hopefully we will have submarines in these places, and it's going to be so freaking cool when we go look around. And maybe we'll find nothing, which would be another really interesting data point. Or maybe we'll see stuff swimming around, right? Whether it's single cell stuff or more, so
We got another question here. Hold on a second. Let me get the microphone to Dave Giltynan.
okay.
Incredible talk, just riveting. Thank you so much. My
Cool.
question is the current generation, the next wave of Jupiter missions.
Yep.
What are they going to do in terms of looking again at Jupiter's core? There was that fuzzy core thing earlier. The reason I ask, there's been some buzz about exoplanets like K2360 that are that may well be the core of gas giants. This particular thing is a super Earth with a density higher than lead, like 11 grams per cubic centimeter. They think the only way, So
Yeah.
I'm just wondering about that. What's up with the core of Jupiter? Any further studies?
Good question. My honest answer is I have no idea. So unfortunately, because I'm not right, this is not my specialty domain. So from what I was reading, other than, we're going to do gravity missions, right? So all these missions, whenever you're orbiting any of these bodies, you're going to get a lot of good gravity data that tells you, and the more gravity data you get, the more you can kind of differentiate. So let's go back to that core picture from Juno, right? So this stuff, like the reason we even can draw any kind of diagram here, right, is that as you gather gravity data from flying around and you see how the planet tugs on your spacecraft, the more and more you fly by, the more you can resolve effectively like what we call love numbers, right? Like the dimensionality of the core, right? And so you can start distinguishing like the kinds of layers there might be in the planet, whether the outer layer is less dense than the inner layer, like you can start inferring structure. And so we're just gonna get with all these missions, but I don't know, I haven't boned up on that part of the, like, what's it gonna let us tell us, what's that gonna let us like infer relative to what we know today. But good question. Sorry, I can't answer it.
We got another question. Hold on a second.
Mm-hmm.
Tom Black.
Has there been much discussion at JPL about the implications of Starship and having very low launch costs?
Yeah, no, so there's definitely, we're all kind of licking our lips, right? Like waiting for that to happen. So we've had multiple studies. I've actually taken part in some of them, like starting to think about what we could do with that. It's still a little early, right? So we're mostly still just busy focusing on like trying to build the systems we have, but there are, we're starting to spend like a few $100,000 kind of, numbers on, hey, if launch costs are super cheap and we have these large volumes, not just Starship, but even Bezos, the New Glenn, right, has a 7-meter fairing, also supposed to be pretty cheap. And so, yeah, I think the hope is that with effectively near zero launch costs, right, relative to the cost of the rest of the mission, that we can do cooler things and have like real spaceships, right? Like everything we've chucked out there so far, like we're kind of like barely having that propulsion to do the mission. We have to like baby the spacecraft all the time. We have to really watch the mass, right? So it gets really expensive. So what we're hoping to do is launch large things with huge propulsion systems, maybe giant solar arrays, and really do cool, kind of more like Star Trek class science, right? Where it's like you have a real spaceship that can just explore a lot of places. But figuring out how to make that spacecraft cheap, right, is the next frontier. Like as your launch costs go to zero, you got to make the bus cost become very cheap, and then make the instrument cost, right? So the instruments are still very bespoke, very custom, take thousands of hours of people's time, work years, hundreds of work years of people's time. And so they cost tens of millions of dollars to build. And so there's like, you got to like whittle down the rest of that chain, right? But, I mean, to your point, like today, like a Mars mission, Mars Science Lab that I worked on in 2012 launch, the Atlas V that we used for that mission was a $300 million rocket, right? And so hopefully in 5 years, if Starship gets going or these other companies kind of do their thing, hopefully that ride to Mars is like 10 million bucks, right? And so you can spend that money on a lot of other cool stuff. Yeah, so hopefully we'll get there, but we don't have concrete things yet. There are advanced studies like doing giant telescopes and other things, but nothing ready to go yet. That's just waiting for like, hey, give me $1 billion and I can go build this gigantic 30-meter telescope in space or whatever, right? Just at the beginning part of that thinking.
All right, we got another question coming up.
Mm-hmm.
I super enjoyed your talk. I've got a couple of, or just a main question about Jupiter and Mars, since I was looking over your resume a little bit beforehand.
Okay. Yep.
That's part in your wheelhouse there.
Yep.
You mentioned the intense radiation environment of Jupiter and the electronics, and I guess, you minimize the dose by flying through the inner system of Jupiter very fast.
Yeah.
I have a recollection, and maybe you can correct me if I'm wrong, that the Juno outreach camera was mainly off the shelf.
It is.
So I want to add that to the recent Perseverance mission to Mars, which I'm sure you're much more familiar
Yep.
with than I am, and specifically the Ingenuity helicopter, and
Yeah.
it's also using COTS electronics versus radiation hardened stuff. And I guess I'm wondering if there's been, I understand the need for rad hard stuff for, multi-billion-dollar probes, but is there a realization at JPL that
Yes.
maybe sometimes you can get away with cheaper electronics?
No, yeah, excellent question. That is a very active area, right, that we're looking at, and we're trying to collaborate with other commercial space companies on this stuff. And so, yeah, as you said, clearly there's evidence that maybe non-rad hard parts can actually last. And it's actually, I mean, that's a whole nother rabbit hole we can spend an hour talking about. It turns out, right, a lot of the rad hard parts, it's like maybe it's worth a minute, right? It's kind of interesting, right? So the military obviously also has a need for rad hard parts, but it turns out dose rate matters a lot, right? And so like how fast you accumulate the radiation matters a huge amount. And I think we've just been kind of learning about that. Or I mean, maybe we've known it, but we haven't been able to take advantage of it, right? So obviously for a military, if I'm building a military spacecraft that I want to survive a nuclear attack, right? Like the Russians or the Soviets back in the day, launch a nuclear missile and try to blow up my spacecraft, right? That's a very, very, very high dose rate event. And so when we talk about like total ionizing dose, I want a part that can handle 100 kilorads or 300 krad. It's not just 100 or 300 krad. It's like, and it's going to see those 300 krad in like 5 seconds, right? And so that's what we kind of, when we think about the outer planets and these high radiation environments, we're like, oh, wow, we have to have these high radiation tolerant parts. But it turns out if you lower the dose rate, a lot of different kinds of electronics chips, right? Even non-rad hard ones, they basically heal themselves. Like there's kind of like, especially when they're warm, there's a healing rate, right? So like you have a curve for healing for a lot of circuits, not all, and a curve for like dying from radiation. And so I think what we're seeing with some of these commercial parts is that the healing rate is keeping up with the dying rate, right? but it takes a lot of money to test all these parts and figure out which ones that's really true for and all that stuff. So we're starting all that activity. And anyway, so there's a big move in that direction, and we're trying to leverage like automotive parts. Like there's a big push by both, I think, NASA and soon and already commercial space to leverage automotive parts, which have really great quality control, at least some of them, right, and stuff like that. So yeah, we're trying to move there. Again, part of that bigger picture of like, how do we lower the cost of the whole thing now that launch is becoming cheap, right? So hopefully it wasn't too long-winded.
All right. Hey, can you see me here, Daniel?
Yeah, sure. Yep.
Good. Okay. So first of all, if I knew you had to put that much effort into it, because Daniel said to me, what do you want to hear about? And I was like, oh, let's talk about this. I didn't realize it was going to take the amount of time.
That was awesome. I really enjoyed this. It was a lot of fun to put together. So, like I said, I'm a space nerd, and so I don't mind.
Well, we loved it here. I can tell you that we had a great time. So again, round of applause for that.
Yeah. Yeah, you're welcome. It was a lot of fun.
And what we'll do is within about the next week, we're going to send you this fabulous Cass, the coveted Cass coffee cup, and we'll mail that out to you. Can you see that?
Oh, cool. Oh yeah, sweet. Okay.
Yeah. And
awesome.
on the back, it's got some major meteor showers. Let's see. I don't know what year it's from though. But anyway, yeah.
It's got the dates. Okay, sweet. Yeah, nice.
But in any case, thank you so much for doing this. This was fantastic. I'm going to see if I can get connected up with NASA again, maybe to do one of these things for next year. And but this was great. This was fabulous. Yeah. And yeah, absolutely.
Yeah, my pleasure.